Welcome back after lunch. Now Goutham, Gopalakrishna will talk us about deep learning and microfinance, neural nets, and all these things you need to know going forward. Goutham.
All right, thank you. Thanks everyone for being here. Thank you, Markus, for this opportunity. I was part of this initiative as a student before, so it feels nice to be presenting here. For those of you who don't know me, I'm Goutham. I just graduated from Swiss Finance Institute, and I joined Rotterdam School of Management as an assistant professor. I'm going to talk about deep learning and macrofinance today. The talk is split into two parts. In the first part, I'll just talk about neural networks as a function approximators. So the first part is going to be basics. And then in the second part, I'll talk about how to use neural networks to solve macrofinance models, typically the models that you saw in the lectures in this Princeton initiative. All right, even though machine learning is fairly new, it has gained momentum in the past 2 decades, but the idea of this goes all the way back to Rosenblatt 1958, who introduced the idea of perceptrons. What are perceptrons? These are simple functions that takes as inputs and throws binary outputs. Okay? Back in the days, it was popular, but then the progress largely halted during the 90s. There are 3 big reasons for the revival of machine learning literature. First is the availability of data. To properly train deep learning models, you need lots and lots of data. Right? Second, computational power has also become much cheaper now. You all have access to free GPUs, even if you don't know it, because Google Colab is free. Right? You don't need to purchase architecture. It's there on the cloud for you to access it for free. Third, there are lots of advancements in machine learning algorithms, in particular how to optimize these parameters in high-dimensional spaces. All these 3 things combined has revived this literature, and particularly there are lots of interest in the industry where packages like TensorFlow, PyTorch, and JAX these days are being built by the best software engineers of our generation. So these tools are readily available for us economists to just borrow and use it for our models. There's a strong community support, and these are the reasons why machine learning will be the future, at least for some point in time. All right, so let me start with a very simple introduction of deep learning. Okay? Let's think of a simple function, y equals f of x. X is a vector. Y can be a vector, but let's think of a scalar in this example. And if you think about basic econometrics, this is a regression problem. But in macroeconomics, f can be a value function or a policy function, and x is the state space, right? All right, so how do we approximate this function given the data points vector x? I'm going to use a simple artificial neuron, okay, which is depicted here. This artificial neuron takes in inputs as a vector x1, x2, and x3 and does a linear aggregation. Okay. The linear aggregation is simply this component here. Once you apply linear aggregation, you feed it into a nonlinear activation function. Okay? That's depicted as a neuron here. Out comes y, and the hope is that the y will be a good approximator for this x. Okay? This is simply a representation. For now, there is no learning. This is how you would represent an artificial neuron. Okay? Now, why am I showing you this? Because this is a fundamental building block for a deep neural network. Okay? Deep neural network is basically a collection of these neurons, these simple neurons, with its own parameters typically captured by weights and biases. Okay? So let me talk about a feed-forward neural network. There are many types of deep neural networks. This is the most basic one. It's called a feed-forward neural network. In large language models, you might have heard of LSTMs and RNNs. Those are very different. But for today, I'm just going to talk about this simple structure. Okay? All right. What do we have here? We have a vector x, which is the input. There are L hidden layers, and there is one output layer. In this case, the output is a vector. Okay. All right, the hope is that we want to approximate this function f using the input x by feeding through these neurons. Right? A bit of jargons. This is what architecture is all about. It's about what kind of neural networks are you using. In this case, it's a feed-forward neural network. How many hidden layers do you have? How many neurons do you have in each layer? and what is the activation function that you're using. In this case, the activation function is simply sigmoid activation function, right? The convention is to use same activation function in the hidden layers, but in the output layer, you might use a different activation function. For example, if you're solving for the marginal utility, then you know that it's going to be positive. So you use a soft plus activation function in the output layer because that's the economic information that you have that you can feed into the neural network structure, architecture in particular. Okay? All right. So let's talk about linear aggregation. Yes?
So I thought that the value of activation functions was considered to be like faster and more efficient to train these models.
So that's a good question. In computer vision, ReLU activation functions are particularly popular. But when you solve partial differential equations, which is what I'll get to in the second half of the talk, it turns out that sigmoid or tanh activation functions typically work much better. Okay? One of the reasons is because you take derivative not only with respect to parameters, but also with respect to state spaces. So it helps to have a nice and smooth activation function. OK. So how do we aggregate? Well, I showed you aggregation for a simple neuron before. We apply the same concept here, except that there are multiple neurons. From each of these neurons, you can think of the neurons in the first layer as the input data. From each of these neurons, you take the weights, which is the parameter of this neural network, and you aggregate them and feed into the activation function, right? So there are two components in each neuron. First is linear aggregation, and then nonlinear activation, right? Now, what do we do with this? The output from the first hidden layer serves as an input to the second layer. That's why it's called as a feed-forward neural network, right? Finally, you have the output layer, and you apply a soft plus or other activation function, and out comes y hat. Okay? All right. So why is it feed-forward? Like I mentioned, you're kind of moving in forward fashion. Whereas in LSTMs or recurrent neural networks, there will be connections between this neuron and all kinds of crazy things. But here, you do linear aggregation, nonlinear activation function, linear aggregation, nonlinear activation in a sequential fashion. Okay? I'll talk about why doing this lots of times is important, because you end up changing the geometry of the state space. All right? Any questions? OK, so far it's basic. How do we represent it mathematically? We have it here. H represents the hidden layer. Oops, sorry. H represents the hidden layer. You feed in the input, and this is the aggregation. You plug in the aggregated quantity into a nonlinear activation function. All right. So let's think of a simple example. You have input data x and output y. Y can be a vector as well. And the model is represented this way mathematically. You start from the innermost layer, which is here. You do an aggregation, and then you feed it into an activation function. And you keep doing this twice, because there are two hidden layers here. All right. Now, one thing to notice here is that the parameter vectors, W1 to WL and B1 to BL, is actually very high dimensional. And the reason is that this W is actually a matrix, because each neuron here is communicating with each other neuron in the next hidden layer. So you have lots of parameters. Okay? So it's a different world from projection methods that you might have learned in grad school, where there are complex basis functions, but few number of parameters. But here, it's heavily parameterized system. All right? OK. Now, so far, I've not talked about learning. This is just the architecture. You have some data. You feed in. You get output. Possibly, the output is going to be garbage because we have not learned. Okay? I will talk about learning soon. All right. Before thinking about how to train this, let's think about why deep neural network works. Why do we need this? You already learned projection methods and other kinds of methods. There's Gaussian processes, so on and so forth. Okay? There are two ways to thinking about why deep learning works. First is it finds informationally efficient representation of data. If you are an econometrician, I think that's very helpful. That interpretation would be very appealing. I think for macroeconomists, especially if you want to solve value functions and policy functions using neural networks, I think the second representation makes much more intuitive sense. When you use deep neural networks and learn, what you end up doing is that you apply a series of tensor operations, which are simple tensor operations, but you apply it lots of times, and you end up changing the geometry of the state space, right? These chains of affine transformations, by changing the geometry of state space, makes your life easier because it's much easier to optimize in a simpler geometry compared to a complex geometry, complex manifold that was originally there, all right? This might be hard to think, but let's think of a simple example which comes from François Chollet of Google. Okay? I don't know if I have a piece of paper. Maybe I do. Okay, I'm going to do a crumpled ball just like you see in the figure. Okay? So I showed you what feed-forward neural network is. So what are you doing when you're doing this linear aggregation or nonlinear activation function? Let's think of fitting this ball. Okay? This is actually a complex problem because it's a crumpled piece of paper. If you ask a physicist, they will tell you, to use complex basis functions and use projection methods to solve it. That's one way to do it. But another way to do it is to do a series of tensor operations. What you do is you just start randomly, and you just pull, and then you twist, and then you pull, and you twist, and you keep doing this repeatedly. When you do that, you end up changing the geometry of the state space. Right? It's much easier to do the optimization there. Okay? Now you see why to do these simple operations repeatedly. Just stretching and pulling once is not going to do the job. Okay? You do these simple operations repeatedly. So that's the key for why deep learning works. All right. Let's pause and compare it to the projection methods that we are also fond of. Now, I already talked about the trade-off earlier. In deep learning, there are lots of parameters. Whereas in projection methods, the basis functions is complex, but there are very few parameters. So that's the trade-off. Okay? And one of the reasons to favor deep learning is because we know how to optimize efficiently in high-dimensional manifold. Earlier, it wasn't possible, and that's why people used projection methods, because there are only few parameters to find. Right? Okay. Now, yeah.
This Chebyshev polynomial, is it like having just one layer and different activation functions? Is it equivalent to that?
It is equivalent. It's having just one layer, having a complex activation function, few number of parameters. It's equivalent. Yeah. So potentially, one could also use Chebyshev polynomial as an activation function. Okay? But it's computationally costly. Okay? And that's why people use simple activation functions like ReLU, whereas in this case, we are going to use a tan H activation function. Because the idea is to reduce the computational overhead, because you end up repeatedly doing the same operations many number of times. Okay. All right. Any other questions? Yeah.
How should we think about like the curse of dimensionality here for deep learning? Does it suffer from it?
Yeah, that's an interesting question. The curse of dimensionality, there are many aspects to it. Okay? When we abstract away from the economic problem and just focus on deep learning, then the curse of dimensionality is not that much of an issue. Precisely because we have optimizers like stochastic gradient descent, which I will talk about later, which are very good at handling optimization in high dimensions. Okay? The second curse of dimensionality has to do with the economics of the problem. There are some potential issues. But I will address that in the second half. Yeah?
In terms of what, are there any theoretical results we have, like that ensure the approximation works in some sense? And how does that depend on the depth, say, and the kind of the number of parameters?
Yeah, that's a good question. There is a theoretical result called universal approximation theorem, which tells you that you only need one hidden layer to approximate any Borel measurable function. Okay? Doesn't need to be continuous, doesn't need to be differentiable. In the limit where the number of neurons in the hidden layer goes to infinity, you can approximate anything. Okay? But experimentally, it's not enough to just have one hidden layer. because the idea is, again, to do series of simple tensor operations. Okay? Yeah. Experimentally, we know why deeper layers in it, layers are required, but theoretically, just one hidden layer is enough. Okay? All right. Any other questions?
Is there any ballpark estimate if you use one layer versus two layers? How many fewer parameters you can?
That's
you can approximate well with 1 million parameters in one layer. And how many parameters would you need in 2 layers?
That is a very good question. I don't think I have a good answer to that now. So it depends on, again, on the problem that you're solving. In some cases, it may be that the advantage from using 2 layers versus 1 layer is not very high. But in almost all cases in economic problems, it's much better to have at least 4 hidden layers. Again, I think it's an open question for theoretically understanding why that is the case.
But practically?
Practically, for economic problems, for sure, we need at least 4 hidden layers. Yeah.
Sorry, just one more question on the projection method. So, like, you have these old results, but like you can do projection models with more parameters than variables. If you add like penalty, like add a quadratic constant, like that. And if you go with a single layer analogy, you could, in theory, just do a single projection layer with a lot of. Is it something that just doesn't work well in practice? Is that the issue?
Again, with just one hidden layer, it's hard to transform the geometry again, right? You can add penalty and you can add lots of parameters, but you're still, imposing a shackle on yourself to approximate that crumpled ball without transforming the geometry. Okay? Again, that's the key, and that's why you need deeper layers. Okay, great. Where were we? Let's compare this to more advanced methods rather than just projection methods. I think Gaussian processes and adaptive sparse grid methods are very popular. Gaussian processes can handle up to 10 dimensions very efficiently, in fact, faster than neural network-based methods. However, it cannot handle large amounts of data, so that's kind of a limitation. Question? No, oh, sorry. So adaptive sparse grid methods are good as well, but then once you have non-convex state space, it doesn't work very well. There are 2 alternative deep learning-based methods. One is based on simulation. You can just simulate for the ergodic density and draw training points from there and feed them into the neural network. But it has some limitations. If you want to solve for global dynamics where some constraints are binding far away from steady state, then it becomes problematic to use that method. So I'll mostly focus on the second half on some active learning-based deep learning, which pretty much ticks all boxes that you see. All right. Let's step back and think of a simple problem to understand how do we learn. Okay? So far, I've talked about architecture, comparison to other methods, and why deep learning works. But how do we do deep learning? How does Adam optimizer or stochastic gradient descent optimizer actually learns? For that, let's go back to a very simple problem. You have input parameter x, input space x parameterized by theta, and you want to approximate this function f using an artificial neural network. Again, we are going back to just one neuron, right? The architecture here is one neuron, one hidden layer, sigmoid activation function. Just 2 parameters, 1 weight and bias, all right? The goal is to fit these 2 data points. Trivial problem. The first thing that you need to specify in a deep learning method is loss function. Okay? And in this case, let's just use a simple mean squared error loss function. All right. So can we just handpick W star and B star such that we can fit these 2 data points using sigmoid activation function? Just randomly start with 0.5 and 0. It kind of works well, but not quite. Okay? But how do we know how lousy this fit is? And that's where the loss function comes into picture. Okay? Use the loss function to basically quantify how bad the fit is, which sounds basic, except that this loss function gives economists a lot of room to play with. Okay? For example, for some reason as an economist, that this is the most important point. Okay? In that case, you can just open up this loss function into two components, one for this data point and one for that data point, and attach a higher weightage to the fit of this data point. Okay? All right. In this case, let's just assume both are equally important and move on. This data point, this W and B is no good, so let's try something else. Turns out that it's even worse because it perhaps helps to move in the opposite direction. Okay? So let's move in the opposite direction, and we keep doing this until there is convergence, where by convergence I mean that this loss is close to 0 in a mean squared sense. Okay? All right, more principled way of doing all this guesswork is actually what deep learning is all about, especially when it's not an artificial neural network, but a deep neural network, right? Cool. So why do we need deep neural networks? It's because I showed you a simple problem, but in many real-life examples, the problem is quite complex, and your loss function may look something like this. Okay? It's hard to navigate and find a global minimum, and that's why you need better optimizers. This is just in 3 dimensions. Imagine 10,000 dimensions, then you need really good optimizers. Okay, let me talk about 2 or 3 most commonly used optimization techniques. Okay? I think most of you are aware of what gradient descent algorithm is. If not, the algorithm is fairly straightforward. It starts from a Newton method that we learned in high school. Right? Start with some arbitrary weight W as an initial guess, and you want to update this weight by looking at the gradient with respect to the weight W, the gradient of the loss function with respect to W. So this delta, inverse delta W means dl over dw, where L is the loss function, right? You also do that for the bias, and you keep doing that until convergence. Okay? By convergence, I mean the L2 squared distance between L2 norm distance between WT1 and WT is as low as possible. Okay, so this is the gradient descent algorithm. If you want to apply it to the previous example that I showed you, you take the problem, you take 2 data points, you compute the derivative with respect to loss function, and you aggregate them. Okay? This is trivial, but why am I showing you this? Whenever you do these kinds of simple arithmetic in computer science, you should think about memory implications. Okay? Going back to the first slide, I told you deep learning only works when you have lots and lots of data. Okay? So what happens when this, instead of 2, you have 1 billion? When you have 1 billion data points, you end up computing these derivatives for each of the 1 billion data point, and then you aggregate. And then you update the weight. Okay? So basically, you have to go through 1 billion data points before you update the weight and bias once. Okay? And that's a huge memory implication, and we have to think about ways of resolving this problem. Right? Any questions here? Okay. So this is how the algorithm will look like. You're not going to code as an economist any of this, but it helps to know what these techniques are, so that if you want to play around with this, then you have to get to the core of it. All right, first you define the activation function, and then you define your loss function. What is loss dependent on? It's dependent on the parameters of the neural network. In this case, it's just W and B. Okay? Once you have the parameter, you compute the gradients with respect to the parameter. Why? Because we need this to update the weight and bias using gradient descent, right? All right, that's what you do in the final step. Okay? This is the key part here, where for each data point in your sample, you compute these gradients, and then you finally update the weight and bias. Okay? Here you can see memory implications. If you have 1 billion data points, this is big O of n, which is still very large, right? All right, so how do we get around this issue? So we use something called stochastic gradient descent. Okay? In stochastic gradient descent, instead of going through 1 billion data points and then updating weight and bias, you just look at each data point and update the weight and bias, all right? But then that introduces a lot of noise. The true gradient is actually the sum of the gradients, but here each gradient is favoring the data point that it's working on, right? So that's where the stochastic nature is coming from. All right. I think when you compare these two methods, you can see where the memory implications are, right? In the plain vanilla gradient descent, you're going through each and every data point, computing this delta W, and then updating it. Okay? Whereas in stochastic gradient descent, you're pushing this update into the loop here. So you see a data point, and then you update. You see the next data point, and then you update. Now, this is also problematic because it's way too noisy, right? Each update is favoring the data it's actually working on. So there needs to be a middle ground between these two. And the middle ground is mini batch gradient descent, and this is by far the most widely used method today in machine learning. Okay? What is mini batch gradient descent? Well, looking at 1 billion data points and then doing an update is bad. Looking at just one data point and doing an update is no good either. The middle ground is just look at, I don't know, 100,000 data points and then do an update. Okay? You take the entire sample, you split it into 10 or 20 or whatever, and then for that mini batch, you upgrade your weight and bias so that you navigate this problem. All right? Okay, any questions so far? Yes?
Yeah, so you know obviously much more about this, but is it only about memory? Because in principle, I could also just accumulate gradients first in the first thing and then update in the end. I thought the stochasticity also helps you with some other stuff. Like
yes. Yeah, that's a great question.
The memory thing, or do you think there's also other?
I was going to get to it. The second major advantage of doing this is you're less likely to be trapped in a local minima, I think, which is what you're referring to, right?
That was the only thing I had in mind, but okay.
Sure. When you use these stochastic gradient descent, or when you use this plain vanilla gradient descent, it's very easy to be trapped in local minima. Okay? I think it helps if you visualize the loss function, the nasty loss function that I showed earlier. Okay? However, when you do this upgrade of these parameters by looking at different data points in different samples, then it's very easy for you to converge to a global minimum. Again, I'm not aware of theoretical results that show this, but experimentally it's shown to work much better. Okay. Yeah?
What's the counterpart of observations when you're trying to do value functions and stuff? Is it like the grid space? That's what your end is?
Sorry, can you say that again?
So like with data, I understand it's like you have like a billion observations.
Yes.
Like when you're trying to approximate functions, is that like the number of points you have on the grid space?
Oops. Yeah, when you approximate functions, you just simulate from the state space, and then you feed in those points. Okay? Actually, that's an important point because in function approximation problems, one way to do is just feed in the entire grid, like how you do finite difference methods, right? Another way to do is to think of them as some state space, and you can draw as many samples as you want in order to fit the function. Okay? The latter is better because deep learning works better when you have lots of data. Okay? All right. Okay, there are no more questions. Let me just talk about more variants of these optimizers, but I'm not going to show you the algorithm. By far the most popular optimizer today is Adam optimizer, which is here. Okay. What it does is, so far in the gradient descent that I showed you, the learning rate, the size of the update is kind of fixed. Okay. When you go back here, this eta is what I call as the learning rate here, is fixed. Whereas these optimizers also play around with the learning rate. Okay. There's something called momentum gradient descent, which I didn't show you, but it's in the slides if you're interested. It increases the speed of your descent depending on where you are on the loss surface. When you're on the top of the loss surface, it helps to move faster, right? If you're repeatedly making changes in the same direction, perhaps it's a good idea to move faster. So that's the idea that momentum captures. Okay. Adam also captures that, but it also adjusts learning rate to capture sparsity in your state space. Okay? Imagine a regression problem. One of the dimensions has very sparse data. Okay? But as an economist, you know that this sparse dimension is actually very important. Okay? So it's important to get a better fit in that sparse dimension. However, when you simulate and feed in the data, the optimizer is not going to see this data many number of times because of its sparsity. Okay? So perhaps it helps to take this into account and adjust the learning rate such that you're paying more attention to that specific dimension. Okay? And that's what Adam does. Right? On the top of momentum, it also pays attention to sparse dimensions. All right. This is how the update rule looks like. But again, it looks a bit nasty here, but it all goes back to the stochastic gradient descent algorithm that you saw earlier. You have the update equation here, okay? And you're tampering with the learning rate to pay attention for sparsity. And instead of delta W, you have a momentum term. Okay. Perfect. So one more jargon you have to be aware of is backpropagation. Okay? So what is backpropagation? I told you that to compute delta W, you need a loss function, right? It's dl over dw. Okay? But how do we traverse through the network to compute this loss? That's what backpropagation does. It's basically an application of chain rule. Okay? To understand that, take a simple artificial neural network. You saw how to train this network with no hidden layers and just one neuron, right? This is the loss function, which can be a mean squared loss or binary entropy loss or whatever. And you just compute this derivative in closed form. This is simple in just one neuron, but what if you have lots of neurons? Okay? You basically do the same thing by applying chain rule and you aggregate. This procedure is known as backpropagation, just a jargon that you need to be aware of. Okay. All right. I talked about this briefly before. Neural networks are good function approximators. The theoretical result comes from universal approximation theorem. A network with just one hidden layer is enough to approximate any Borel measurable function. Okay. Yeah? It doesn't need to be continuous. Just has to be measurable. That's all. Yeah, if you have function with jumps, you can approximate it. Okay. So experimentally, however, having just one hidden layer is not enough, like I explained earlier. So people typically use deeper neural networks. Okay? The problem here is there is no clear guidance on the right architecture. It depends on the problem at hand. Okay? One starting point is to use the right activation function. In computer vision, it's popular to use ReLU activation function. But if you use ReLU, it doesn't really work well when you have these partial derivatives. So it's shown that a sigmoid or tan H activation function works much better. Okay? There is, again, no theoretical guidance for this. That's one major limitation of these methods. But we can leverage on what other people find in this literature and start with that architecture. Right? Okay. So one of the limitations that I talked about earlier, there is no theoretical guidance. There is also requirement for lots of data. This can be a limitation in some fields, but then for the problems that I will show you in the second half, that's not a big issue. And one of the reasons is you can just simulate as many data as you want. Well, you have the state space at hand. Just simulate billion points. If that's not enough, simulate 2 billion. There's no problem with that. Okay? As long as you have good optimizers to handle high dimensions and high data, that's not a limitation. Yeah?
I just wanted to get some intuition on this big data. So like with projections, I understand, if like asymptotics, there's noise in the data, so you want more observations to like see through the noise, pick up the parameters. And data space, that kind of makes sense to me. But over here, like you can like kind of generate the data pretty noiselessly. So it's not clear why more data is helping you that much. Is it just that the function might be locally very funky, and so that's what you're picking up when you do more simulations?
That's a good question. Partly that, but another reason is also for mini batch of stochastic gradient descent, it helps to get different kinds of data to avoid the local minima trap, right? Yeah.
Yeah, also I have a related question. So since we already can simulate data, what is the point of deep learning? So is it to have some interpolation, you can have some smooth function over the whole space? So is this why we need deep learning here? Or?
Some functions are hard to approximate with traditional methods. Okay? And that's why we need deep learning, because it helps, again, by transforming geometry such that it becomes easier to approximate even really complicated functions. Okay? And
if we have some data point, we want to know the value of the function, we can simulate the value at this data point, right? So, yeah,
sure.
So why do we still need the deep learning?
Sure. In some cases, you don't know how the function looks like. You don't know where the nonlinearity is. You have no information about the function except that it obeys some partial differential equation, for example. Okay? In that case, you would be, there is no other traditional way that will tell you what the function will look like, right? So in those cases, you just sample from the state space, and you find f hat that obeys this equation, and that's your actual function. That approximates your actual function. But I think this will become concrete in the second half. Yeah? All right. Yeah.
It's also related to questions like functional basis is notorious for extrapolation, but sometimes when we want to do counterfactual, we want to do extrapolations. So for deep learning, can we get any confidence in extrapolation?
That's a good question. In fact, deep learning is shown to be very good at extrapolating. And one of the reasons is that by using these stochastic gradient descent methods, you're kind of minimizing the noise even out of sample. Just forgetting deep learning, going back to basics of machine learning, we know that it works very well out of sample in regression problems, right? Similar logic applies in deep learning as well. However, it relies on how efficiently you train. If you chase noise quite a lot, then that's not the case. 2 questions, I'll start with you.
But don't we need to use like regularization techniques to prevent overfitting?
Oh, that's a great question. I'm going to talk about regularization, but in a very different sense. Okay? In machine learning, people use penalty functions as regularizers, but I'm going to show you, you can also use some economic information as regularizers. Okay? It not only helps to discipline the learning process, it also helps in faster convergence because you're encoding the economic information. Yeah? Question? No? Okay, sorry. All right. Third limitation is that sometimes learning can be very painfully slow if you don't have access to a high-performance cluster. But I think few years down the line, that's not going to be a major limitation. Already, we all have access to GPU. Soon, we will have powerful access to TPU or whatever. So the third limitation doesn't worry me a lot. OK, there are lots of under-the-hood details, which I possibly cannot cover in 1 or 2 hour talk. If you're interested, there is a mini course on deep learning and macrofinance models, which is generously hosted by the Bendheim Center, and it's available online, which you can take a look here. Yeah.
Does the method assure convergency? Like, do you know that the loop is going to stop at some point, or in theory it could run forever?
That's right. You don't know for sure. So what is convergence in these problems? That your empirical loss is as close to 0, yeah. Right? But what is as close to 0? If you just specify 10 power minus 3, is that as close to 0? Probably not, right? So you just keep monitoring the loss. And as long as it's less than an acceptable threshold, which is 10 power minus 5, for example, for the economic problems, then you can be sure that you've converged. Okay? Yeah?
But could the loss stabilize before reaching 10 minus 5?
What do you mean by stabilize?
Like, because the standard methods, you don't have assurance of convergence, right?
Sure.
Unless you have like global uniqueness. So
because the gradient will converge to 0, right?
What?
The gradient will converge to 0.
Yeah.
And then you're stuck. If your gradient is at 0, you're stuck.
in a bigger model?
So if there are chances that your gradient will become 0 and you haven't converged, right? That may be your worry, which is true. It's called navigating the plateaus. That's where I think stochastic gradient descent helps. Because it's very unlikely that you do this mini batch 200 times and then every single time you're stuck in a plateau. That's very, very unlikely. Okay? If you're stuck in a plateau all 200 times, then it means that you've actually converged. Okay? All right. Okay, I'm going to jump into the second part. Any more questions on basic deep neural nets? Now we are jumping into macrofinance. Yeah.
Previously, you said active learning is superior to simulation in the sense that it solves the problem more globally. So, what is the difference between these two different kind of deep learning?
Yeah, that's a good question. If you can hold on to it, I have a slide with a concrete example. If it's not clear, just come back to me. Yeah. Okay, let's move on. So I'm going to talk about one of my papers, which is a methodology paper, where I built a machine learning-based technology to solve a broad class of models in continuous time, particularly to solve these models globally. Right? The way it works is I use neural networks as to solve supervised learning problems. It can particularly be applied to portfolio choice problems, macrofinance problems like the problems that you saw today, and also monetary problems. It works by encoding economic information as regularizers in the neural networks. Okay? And it learns the subdomain of the state space that carries the most economically relevant information, and that's the active learning part of this. Put together, this technology is called aliens. Has nothing to do with actual aliens, just an abbreviation. All right, so let's start with the general setup. Think of a representative agent who has this utility. F can be a recursive utility. That's why U here depends also on U. The goal is to maximize this utility subject to a wealth constraint. Before that, the agent has access to a risky asset as well as a riskless asset. The risky asset is a claim to this dividend, which is exogenous, follows geometric Brownian motion. Right? And the problem of the agent is to maximize this lifetime utility subject to the wealth constraint, which evolves like this. I think by now, I think you're familiar with how to derive these wealth equations. Now imagine that this G, this sigma, as well as this R are exogenous and time varying. Okay? And this is a setup where the opportunity process in the portfolio choice language is also time varying. Okay? Then you suddenly have a high dimensional problem to solve, right? One advantage of using continuous time machinery is that when you solve this HJB, when you write down this HJB equation, it becomes deterministic. If you're in a Brownian world, the shock doesn't appear in the simplified HJB equation, right? It reduces this to this partial differential equation. This PDE can be highly nonlinear because of the coefficients here. Okay? This is called as the linear term. This is the advection term, and this is the diffusion term. They can be all very highly nonlinear. And that's why solving this elliptical nonlinear PDE can be very difficult. On the top of that, the state space can also be high dimensional. Okay? This D can be very large. What has the past literature done? In simple dimensions, it transforms this highly elliptical PDE into a quasi-linear parabolic PDE, okay, by introducing a false time derivative. What it does is it converts these unknown PDE coefficients into known constants here, okay? Because you're kind of freezing these PDE coefficients as they are known from the previous iteration J old. And now the goal is to solve this linear parabolic PDE. Okay? You can just simply discretize this and solve it, which works really well in low dimensions. Okay? As long as you move to 3 dimensions, it becomes very difficult. In particular, this cross partial derivatives create a lot of problems. Okay? All right. Another way to solve this, which I'm going to talk about here, is not to discretize this, but to just use automatic differentiation, a tool out of the deep learning that we learned in the first half, and approximate these derivatives. Okay? And theoretically, this will work well in really large dimensions, and I have a problem where I show that it works well in 4-dimensional problems. Okay? Okay, so how does it work? Similar to the value function iteration approach that you learned in grad school and possibly in this this initiative lecture, you start with an arbitrary value function j. Okay? And then you compute the policy functions. For example, in the lecture that you saw today, it's consumption, portfolio choice, capital price, return on capital, so on and so forth. Okay? Now, once you have that, the goal is to update this j. Okay? Instead of using finite difference, instead of discretizing the PDE and using finite difference, I'm going to use neural networks. Okay? But everything else will remain the same. Okay, makes sense? All right, let's go back to the problem. This can be any general macrofinance problem. Doesn't need to be the problem that you studied today, but it should be fairly familiar. Right? You have this partial differential equation with a advection term, diffusion term, and a linear term, right? And you add a false time derivative. Okay? And instead of discretizing, let's just think of this j hat as a deep neural network object parameterized with arbitrary theta. Okay? And this f is called PDE residual. Okay? Now, because you have this time dimension, it should be satisfied in the time-space domain, where the space domain is omega and the time domain is this. Okay? On the top of that, you have an initial condition. The initial condition has to be satisfied in this domain. Okay? In the first iteration, this initial condition is just arbitrary. Take j equals 1 everywhere, and that's a good guess. Okay? And in the subsequent iterations, the initial condition will be the j hat from the previous iterations. Okay? So by introducing this false time derivative, you're bringing in a lot of stability to the learning process. Okay? What does it mean? You're forcing the PDE residual to be satisfied in the time-space domain, but you're also forcing it to obey the initial condition. Okay? That's where the stability comes in. All right. This should be roughly similar to what we already know from basic optimization. The goal is to get a data fit. This j has to be satisfied in the boundary condition. Okay? And the PDE residual should also be 0. Okay? Why are we doing it? To find the optimal parameter theta. Okay? Because I told you that this j hat is parameterized with theta, but that's not the optimal one. Okay? Now I'll talk about how to learn and find this optimal theta star that satisfies this partial differential equation. Okay? When you do this repeatedly, say 40 or 50 times, this derivative will become 0. That means that the algorithm has converged. Okay? Yeah?
So how do you express this cross-partial derivative with neural nets? I know it's very convenient using backprop with the single partial, but how do you express this cross-partial?
It's as straightforward. So I actually have a code in the end that I will show you, just one slide of code, where you will see that it's very easy to express the cross-partial derivative. Okay? Yeah?
So you can distinguish J0?
Oh, it's the initial guess. The first iteration is a guess, but in the subsequent iterations, it's the j hat that comes out from the previous iteration. Yeah?
So is it possible to minimize f and such that j equals j0? Like a dual problem here.
Yes, that is possible. Yeah, it's roughly the same, right? But as far as the optimization is concerned, that's roughly equivalent. Yeah.
Do you solve it once for each time step, or you solve it
once for each time step?
Once for each time
yes. Now, in simpler problems, you actually don't need this time derivative. Okay? You can knock it off and then solve as if it's stationary. But then neural networks are very good at finding cheat solutions. Okay? What do I mean by that? Imagine there is no time derivative here. Okay? If there is no time derivative, you don't need an initial guess. Okay? So let's knock this off, knock this off. Okay? Problem is to find theta star such that the PD residual is 0. Okay? Neural network is going to tell you j hat equals 0 everywhere. Okay? That's a cheat solution that satisfies this PDE. Okay? Unless you have to enforce learning process to, you penalize the learning process when j hat equal to 0. That's one way to do it. But then what if it finds j hat equals something else which satisfies another PDE that you're solving? So it's kind of a mess. And that's why this brings in a lot of discipline, because you start from a reasonable guess, and then you slowly introduce the nonlinearity. Yeah? Yes?
Can this method deal with boundary conditions?
Yes. You can think of this as boundary condition. Okay? If there's another boundary condition, you can just add that in and add here. Okay? It's as simple as that.
But the way I would do is that I would minimize, but then when I do the next step, I just impose that the function is equal to, suppose I know the boundaries.
Yes.
I would just impose that at the boundaries.
At the boundary, it has to hold. That's what you impose. And you impose it by adding another component here. Right? So whatever data fit that you want, you can feed in here as the objective function. And then your PD residual is the constraint here. Okay? That's one way why I wrote this problem like this. There's a dual problem where you minimize f equals 0 such that this holds. But yeah, it's equivalent.
So if you have 100 periods, you train it 100 times.
Sorry, say that again?
If you have 100 periods, then you train
100 times. That's correct. That's correct.
And when you train it for time 75, you train it presumably from where you arrived at step 76?
Yes, that's correct. That's correct.
So you use already some efficiency that's built in.
Yes. Yeah, that's correct. It relates to transfer learning as well, because you're using what you've already learned from the previous iteration.
You don't train it from scratch.
I don't train it from scratch. Again, in the online course that I showed you earlier, I have code snippets that tells you how to save these models and load them again, which roughly relates to transfer learning, but not quite, but in a similar spirit, let's say.
So then presumably when you train it for period 99, it's a lot slower than when you train it for period 1. Like you train from the end.
If you train from the end, in period 1, it's going to be much faster.
Much faster.
Much faster.
Because you already have a very good...
Exactly. Yes. Any other questions? Yes.
So, tell me if I'm screwing something up. The time derivative, we want it to be 0, and then we want everything else to be 0. That's like our optimal solution, right? Then we've solved the PDE.
You want the residual to be 0, that's right.
I guess I'm curious if the time derivative is quite large, but the rest of the f term is quite large in the opposite direction, then you could still have it equal to 0, but you don't have the solution that you want.
That's right. In the first few iterations, you won't have the right solution, right?
But
you're slowly marching towards the right solution.
And that's just because like the neural network finds like the most elegant solution, which is one in which the time derivative. Like, how do we know that it's slowly marching towards the right solution?
Well, so one way to know this is you solve for the optimal j hat, and in the next iteration, you're forcing it to obey in the time boundary, right? So that introduces stability. So you're kind of anchoring j hat to obey j tilde in the time domain, and then in the time-space domain, it solves this PDE, right? So it has to hold everywhere in the in the internal of the state space and also in the time boundary.
Okay.
Yeah.
And training it 100 times for a parabolic equation works better, you say, than training it once for the elliptic equation.
That's correct. If the problem is very complex. Yeah. For simpler problems, just solve the elliptical problem directly without time derivative. But this is more general. And this works especially well when you have barriers, like the problem that you saw today. Okay, great. Yeah.
And is there a theorem that says that whenever this stops, you got the right solution, or?
That's a good question. So in the paper, I have a result that shows that when the loss goes to 0, this j hat converges to j, but I don't show that this j is the unique solution to the problem at hand. Okay? That's a separate story. But what we can show is when the loss is 0, this j hat approximates j. That we can show theoretically.
Okay, so as long as the PDE has unique solution.
Yes, as long as the PDE has unique solution, you find the right solution. But whether it has a unique solution is a more general problem. Yeah.
So how do you do the gradient descent when you search for capital theta there with a constraint? Because the way you described it, it's some constraint optimization.
Yeah, that's a good question. So you just add that constraint in, right? One way to think about this is like a Lagrangian problem, but that's not how we typically do. You just set Lagrange multiplier equal to 1 if you want. Okay? So you kind of aggregate the loss. Okay? You take this data fit plus you take this residual error, and then you minimize the aggregate. It's kind of like Lagrange multiplier equals 1. Yeah? Okay. So this is what we have. Theoretically, f should be 0, but we do Monte Carlo. In an L squared sense, this Monte Carlo integral should be equal to 0. Okay, so why is this important? How is this different from finite difference methods? The first difference is that it's completely mesh free. In higher dimensions, you don't have to carry around the grid from one iteration to the next. Here you just do random sampling. All right, but that comes with a cost. In high dimensions, what if you don't sample from important regions? What if you always sample from regions that are unimportant to the economics of the problem? So that's where active learning helps, which is the core part of this paper. What the aliens does is it tracks the subdomain omega c. Subdomain is this omega c is a subdomain in omega, which is the state space. It tracks that actively from one iteration to the next and samples more points from there. Because you know that that's an economically important region, and there we want to have a better fit. Okay, let me give a concrete example 2 slides down the line, but before that, the way we would approach this problem is basically encode this j hat using some arbitrary parameters theta using simple feed-forward neural network. This goes back to the lecture that we saw in the first part. This is the simple feed-forward neural network. In addition to the state space, you also have time dimension now. So you feed both of them in here. You use sigmoid activation function, and you get j hat. Now, most likely this j hat is going to be rubbish because we have not trained, right? So what does training entail here? We encode this economic information as a regularizer in the learning process. That's the next step. Okay, so now let me go back to what active learning is. Let's think of a problem where there are 2 dimensions. One is the productivity, and second is the well share of experts, like in the model that you saw today. And this is the policy function or price function that comes out of it. It looks fairly linear when well share is high, and it looks pretty nasty here. And there is a kink involved, and the kink goes in 2 dimensions. If you sample points randomly, there is a good chance that many points come from here, many will come from here, and very few points actually come from there. However, that's an important economically relevant information that you know from this model. That's where some crazy stuff happens and the capital price crashes. Active learning is a way to track that subdomain and sample more points from there. This method is mesh free, so you can just potentially uniformly sample from the state space. However, you pad those training points with these active points. And these active points come from economically relevant information. Why is it active? It's active because from one time iteration to the next, the shape of the economic region might change, and the location might also change. So it's important that you keep track of it actively from one time iteration to the next. Okay? Yes?
Sorry, so my first question is, in each time step, that's basically deep Goutham with this active learning, right? What you're doing?
In each time step, it's not exactly deep Galerkin because Galerkin uses complex architecture.
Okay, like let's say with the feed forward.
Feed forward, yeah.
It's deep Goutham with this active learning.
With this active learning,
okay.
That's correct.
My second question is, how do you keep track of that? Is it like where there's a lot of curvature, you say there's we'll sample more, or is it like a priori given? Or
yeah, that's a good question. So in this problem, once you do the first iteration, you can just inspect the PDE coefficients, and the coefficients will have the policy functions that will tell you this is the important region. Okay. So since you're doing it iteratively, in each iteration you have some knowledge of the problem. Now, what if you don't have any knowledge of the problem? Then you could just look at where the error is the largest from one iteration to the next. Okay. They may not be economically important, but they may be computationally important. Sometimes they are often correlated. Yeah.
So this first approach means you actually, as the programmer, look at it.
Yes.
And decide this is an important region.
Yes.
So this is something problem.
Yes.
Alternatively, this model, you could also understand the model and know there's a constraint binding, there isn't binding. Compute where it starts not being binding, and then use those points around there.
That's correct.
That's probably what you're doing.
That's correct. As an economist, you have knowledge of this. For example, you know that in some region, the constraints are going to be binding and some crazy stuff is going to happen. Then put a band around it and sample more points from there. Okay? And if you don't have this information, just solve the model, see where the error from one iteration to the next is largest, and sample more points from there, because more likely that's where nonlinearity is the largest, and that's where the network is struggling to minimize the error. Okay. Okay. Now, so how do we actually optimize this? Start with the feed-forward neural network. You get J hat. Well, that's going to be lousy. So what do? We use automatic differentiation and compute these partial derivatives. Computing these partial derivatives is very cheap because you're just opening up a graph and placing placeholders. And the reason is you use TensorFlow or PyTorch. You're not going to do this in NumPy or MATLAB, right? When you do that, whenever you perform these operations, the operations don't actually take place. What happens here is in the graph, there will be a placeholder that tells you that whenever I receive an input, I should differentiate it and store the gradients here. So that's all the information that it stores in this neuron. Okay? And that's why it's computationally cheap before you feed in the data to generate these automatic differentiation neurons. Okay? Yes?
One question. Do you also compute the second derivatives, like by back propagation, like twice? Or
That's correct.
Sorry?
That's correct.
So
We use.
But then this graph would work relatively, right? Like if you have 1,000 variables, then the graph is.
Yeah, that's a very good point. Whenever you're computing these derivatives, you're actually kind of enlarging this graph. Okay? So you could do backprop and compute the second order derivatives, but at the expense of growing the graph drastically. But again, using feed-forward neural network is not that big of an issue because doing backprop here is not that complicated, right? Unless you have 15 or 20 hidden layers with 10,000 neurons in each layer, which we are not going to do, then that's not an issue.
Yes, the problem is a bit how many state variables you have. So in the two state variable example of maybe 5, second order derivatives are not that many. If you had, say, a stochastic KFP that you discretize and you have hundreds of state variables, well, you don't want to do that.
That's true. So when you have high number of state variables, also this graph grows because notice here that you're not only computing derivatives with respect to parameters, like in traditional deep learning methods, Here you're computing gradients with respect to state variables. Okay? That's an added curse of dimensionality, going back to the earlier question. So even in those cases, the graph will grow very large. Okay? But then experimentally, we've shown, based on your paper, that up to 50 dimensions, techniques like this can handle. Yeah? 50, yeah. How much does it slow down? That's a good question. I don't have a number on the top of my head, but I can tell you from this example that solving two-dimensional model on a cluster takes you roughly 20 minutes, and going to 3 dimensions probably half an hour, and a 4-dimensional model you can do it in 1 hour. It doesn't grow linearly, so that's the main thing. Yes. Yes, you can have smooth pasting conditions. You just have to, add one more block here and add it as a constraint, right? As a constraint. When you add a smooth pasting condition, for example, v prime of x should be equal to 1 whenever x is x star, then you draw a sample from x star, and then you compute v prime of x star, and you force it equal to 1. By that I mean v star of x minus 1 in a mean squared sense should be as close as 0 as possible. Yeah, as simple as that. Okay. All right, so once you compute these partial derivatives, you just plug into this partial differential equation here, and that becomes your PDE loss. Right? This is your PDE residual. So intuitively, what are we doing here? We are computing j hat, and we are forcing it to obey this partial differential equation in the time-space domain. Okay? Not only that, we are also forcing j hat to obey the previous value in the time boundary. Okay? It has to simultaneously satisfy both of these. On the top of that, you also have active training points. Okay? So you basically do the same things on the active sample, which is what I parsimoniously represent here. Once you do all of that, you compute the loss. What is this loss telling you? Loss is telling you how far j hat is from obeying this PDE. This is telling you how far j hat is from obeying the previous condition, and similarly on the active points. You just aggregate all of the loss together and then use an Adam optimizer and minimize it. Okay? If you have a smooth pasting condition or a boundary condition, just plug it in here. Okay? Add 2 more losses, 1 loss for the smooth pasting, 1 loss for the boundary, and aggregate them together. Okay, the bottom line of this is that you can't expect to just take an off-the-shelf computer science method, throw Adam optimizer at it, and expect it to work. As an economist, you have to use all the knowledge that you know from the problem and encode as a regularizer and use some kind of active learning to guide the learning process. So that's the takeaway from this slide. Okay, so here's another tiny aspect. Now I told you that you can just aggregate all of the components from the loss function, but you can also attach different weights. Going back to the example that we saw in the first part, as an economist, there I told you that if you know one data point is important, attach a higher weight. Okay? So in this example, if you know that the smooth pasting condition is really important for me, then attach a higher weight to that part. Okay? So that's where these lambdas play a role. Okay? One way to optimize these lambdas is a lazy grad student approach. Just plug and play. Try different values. If it doesn't work, just do trial and guess. Okay? A more systematic way to do is hyperparameter tuning, which means you open up a grid, you take several lambdas for each of these laws, solve the model repeatedly, and see where the error is the smallest, and that will be your optimal lambda star. Okay? I think there's even more systematic way to do this by looking at the eigenvalues of these losses, and that has to do with recent development called neural tangent kernel in the machine learning literature, if you're interested. All right. Now, going back to one of the questions we had earlier, why simulation-based method is not used here and why active learning is different from simulation method. Now, let's think of a simple one-dimensional problem. Okay? It's like the problem that you saw today morning. Well share is an important dimension, the only state variable here. And you solve the model, and then you find the stationary density of this endogenous state variable, either through Kolmogorov forward equation or you simulate the model. And this is what you get. Okay? One way to use deep learning method is to draw training points from this ergodic density. Okay? Now, if you look at the problem here, it's parameterized in such a way that all the nonlinearity happens here, okay? Where the ergodic density is pretty low. There's not much mass there. So if you draw training points from the ergodic density, you would end up solving the model only locally, not globally, okay? Because the steady state of the problem, the stochastic steady state, is here. Although the simulation-based methods are also tailored to solve the model globally, precisely because the ergodic density only sits around the steady state, you're forced to solve the model locally. Okay? One alternative way to approach this is to not draw from the stationary density, but draw from throughout the state space in a uniform fashion, which is fine in low dimensions, but in high dimensions, that's problematic. So what do? We draw sparse training points. Don't sample lots of points from everywhere, just draw sparsely. And on the top of that, pad that sparse training points using active points, which mostly come from here. Okay? And how do we know this policy function? Because you use time iteration. Once you solve the model for the first time, you already know this is the most important state space, part of the state space. Okay? So you draw sparse points and then pad those points with active points coming from here. That's the bottom line. Yeah.
So practically, what do you mean by drawing sparse points? And how do I do this
in many dimensions?
So do you just mean uniform here? Or?
Uniformly. You sample uniformly, okay, as much as your computer can handle. Okay? If you have 40-dimensional problems, maybe draw, I don't know, 200,000 points.
Okay, suppose just maybe I have a good suggestion. So here it's clear what I do, because I know eta lives between 0 and 1, it's one dimension, let me just draw uniformly from that thing. But suppose I have a 40-dimensional problem, but I don't know that it lives in the cube from 0 to 1, but it lives somewhere.
Yeah.
So I have to learn something through ergodic sampling in a sense,
sure,
because otherwise I might sample something that never happens, not even in a crisis region. So
that is sure. So that's a great question. In those cases, you combine both techniques. Okay? First you draw uniformly, you solve the model, you look at the ergodic density, make sure that at least 10% of the sample comes from ergodic density, but then also pad that with active points. If you don't know active points, do computationally active points, and then solve the model. Right? You can combine the both. It's not meant to be a replacement for simulation methods, but it complements the simulation methods very well. Okay? The idea here again is that as macroeconomists, we often care about the solution throughout the state space, not just part of the state space where the economy lives in the long run, which is what the stationary density captures. Yeah? Yes?
Can we also enforce active learning for checking the coefficients of the random functions? Like if the derivative is highly nonlinear, then we check the points around the nonlinear derivative? Yeah,
you can do that. In fact, I think one of his papers does that. They look at where the error is the largest, and they sample more points from there. But in their problem, the error is actually coming from the curvature of the value function.
So I think what you say, I just want to reinforce that. So usually, you don't even know where the stationary distribution is ex ante.
Yes.
In some problems, you might have something like a bi-model type of thing, but only if you capture the shape of the value function right. And if not, you miss that. So you're sampling around the middle. You never realize that there's actually some mass to the left that you only get right if you capture the nonlinear.
That's correct.
So that is another reason why you would not want to adjust it.
Yeah, that's a great way to put it. So to paraphrase what he said, in order to get a good fit here, you need to solve the model pretty well here in order to find accurately the stationary density here. That's another way to put it. Okay, any other questions? Yeah.
But if the volatility is endogenous, so you don't know where the volatility is before you solve the value function, how would you? Because then, like, every time you update the value function, the region that you should calculate.
Yeah. In the first iteration, you take a guess for the value function, right? You guess this is the value function, and then you solve for the policy function. In this case, it's return volatility, but yeah. So since you always start from a guess, it's easy to figure this out. Okay? And in the next iteration, you use the improved guess for the value function and can keep marching forward. Okay. All right. Now, I'm going to show you 2 or 3 slides of code just to convince you that it's not as complicated as that you saw in the graph. So imagine you have a one-dimensional problem, and you want to code this thing up in TensorFlow. Okay? You don't need to specify, you don't need to actually write down any of this in TensorFlow. All you have to do is call up a function called neural net, which will come to your rescue and initialize this neural network with weights and bias. You can specify uniform distribution if you want, or normal distribution, and then provide the input here. So minor typo, this should be x. Okay? X and t are the state variables in this problem. This is how you initialize a feed-forward network. Okay? Now comes the regularizer part, that is computing the derivatives and then computing the PDE loss. Okay? How do you do it? This is the function j, and I want to compute the derivative of j with respect to z. You just use this, tf.gradients j comma t. Okay? That's the first order derivative. To compute the second order derivative, you just take the first order derivative here and then compute the second order. Okay? As simple as that. This is going to give you a PDE residual. Okay? If advection, diffusion, and linear terms are also functions of j, no problem. You can just code those functions in TensorFlow. Here, I'm just, for simplicity, I'm assuming it to be constant. Okay? Okay, there was a question about cross partial derivative. How do you do this in TensorFlow? Let's think of a 2-dimensional example, okay? Going from this graph to this graph. Also fairly straightforward. Once you compute these first order derivatives, you just use those first order derivatives to get the second order one, and the cross partial is here. You do j underscore a comma z, as simple as that. Okay? And then you return the PDE residual for this problem. All right. Yes?
So this is also one reason they don't use ReLU, because ReLU, the second order derivative is like, it's 0 like everywhere. So we use the tangent H or the sigmoid activation function.
That is an excellent point. With ReLU activation function, the second order derivatives, the second order with respect to parameter goes to 0. But in this case, since you are differentiating with respect to state variable, that could be an issue here as well. Yeah. Yes?
Maybe this is a silly question, but I was expecting in the function f, so the second one, that you would take in the previous solution.
Yes, you're completely right. This is just for illustration how to compute these gradients. You would actually take this j would actually come from the previous iteration if you want to connect to the macrofinance example that I showed earlier. Okay. Yeah. Another question? Okay. Yes.
In practice, do you think there's like a couple of this TensorFlow, there's like PyTorch, and I think there's JAX. Is there any recommendation you have?
Well, I don't want to stir a fight, but I think PyTorch is very popular now. TensorFlow used to be popular before, but JAX is gaining momentum. The frustrating part about this, to be honest, is you need to pretty much learn everything. Because researchers they have weird preferences, they use different things, and if you want to understand what other people are coding, which is really important in machine learning because it's an open source community, so it helps to be familiar with all of them. But if you're start with PyTorch. Okay. But if you start with TensorFlow, it's even easier because I think it's the more difficult one. If you're very well versed in TensorFlow, the other languages would be very easy to you.
Should we also check JET conversion to some epsilon?
Sorry, say that again.
Should we check the derivative with respect to t converging to epsilon?
That's right. So I don't think you need to check. Eventually, when you do all of this, you would for a convergence criterion, you will do that anyway. You would compare J and J old, and you see how far that is. There you implicitly, that will tell you how big the derivative with respect to time is. Yes, okay, perfect. So few more slides on data parallelism. For models up to 4 or 5 dimensions, I think you can just use your Google Colab account. That's fine, but the moment you go to 40 or 50 dimensions, then it becomes cumbersome. So I think that's where clusters are very helpful. But it's important to understand different kinds of parallelism. Okay? What does parallelism mean? One is data parallelism, and the other is model parallelism. In computer science literature, model parallelism is popular because these language models are so large that it's not possible to fit the graph into one memory. Okay? So they have to split the model into different nodes. Okay? Whereas in economics, that's not a big issue, at least for the type of problem that I showed you today. So here, data parallelism is important. In data parallelism, each CPU core will have the same model because the model is not so large, but the data is huge, right? So you split the data and you send it to different cores. This is your data storage, and each blue box here represents a core. It can be a CPU core. It doesn't need to be GPU. Even in your personal laptop, you have multiple cores. You can just distribute it across the cores. But then it's difficult for these cores to communicate. Okay? And that's where I think Horowitz is very helpful, which is developed by Uber, and they made it available for free. It's an open source package. Each model here will take in the data, different sets of data, optimize, train the parameters, compute the gradients, and then finally these nodes need to communicate to get the total average gradients. Right? And I think that's where Horowitz shines, because they've made it so easy for these nodes to communicate and gather the gradients through an operation called ring all reduce operation. Okay. Once you average the gradients, you just update the model and you keep doing it repeatedly. Okay. So that's data parallelism. And for us, model parallelism is not that relevant.
Each node computes the update step, but with exactly the same average gradient, so that they all keep on having the same model all the time. Is that how it works?
So each time, once the gradients, once you take an average of these gradients, they pass on this average to all the other nodes, so that when you start the next iteration, they all use the same gradients.
So okay. Model is always the same.
Model is always the same, and the parameters are also the same.
That's what I mean by model. So
it's
just the architecture, but literally the parameters are always updated.
That's right. Parameters are also the same when you start, but then when you end, the parameters may be different, but then you communicate and compute the average and pass on the average to the model. Okay?
Is there implicit mini-batch gradient descent involved in this parallelism? Like mini-batch gradient descent, like you see this.
Yes, there is a mini-batch gradient descent running inside in each of these guys. So it's like having 10 computers, but then there needs to be a way for the 10 computers to communicate. Okay? That's why we use this package. Yeah?
Do you not have any lead time issue with different cores working on the same model? Like, do they finish one process at the same time, or do you have to align it manually?
That's a good point, but I don't think I don't think there's an easy way to get that insight, and I'm not sure if that's important as well. Possibly this core is slightly slower, it takes longer, But in principle, all the cores would be equally powerful. So in some cases, the data that you feed in may be so nasty that it takes a long time to compute the average, to compute these gradients. But other than that, I don't see a necessity to track the time difference. OK. All right, so I showed you a bit of code earlier. And I'm going to show you here that using this horovod is not that complicated. You just need to add a few more lines. Okay? You need to pin down a core processor. You can think of it as queen bee. Right? The rank of that processor should be set to 0. And as long as the rank of that is smaller than the number of cores in your operation, just do these gradient descent operations. Once you have that, you just distribute the optimizer, and you session.run.broadcast is basically broadcasting the average that you've computed to all the other nodes, so that in the next iteration, you start with the same model. OK. So how do you use it in a high-performance computer? You just, there is an interactive mode that allows you to open a Jupyter notebook, for example. Just install whatever packages you want. Here you specify the number of cores. There is a time limit involved. It depends on the cluster that your university has access to. Just specify the account name and the job. And once it gets done, you get a message saying that the job is finished. Okay. But I'm just giving all of that so that you have access to slides. And if you want to come back to how to use horovod, you can just pick from here. Okay.
So is horovod just running like Apache Spark or something?
It runs like a?
Is it just running on Apache Spark?
Apache Spark? I'm not sure. I need to check. I don't have a good answer. OK. So I've given a bunch of references if you're interested. There is a nice interactive material here. There's a very good summer school material in a GitHub page by Simon Scheidegger. The lecture notes from Jesus, I think, is also very good. It's available in his website. If you want to take a look at teaching slides, I recommend Hugo's. And for the second part, it mostly comes from my paper, which has a bunch of references. But you can also look at Victor Duarte's paper and Jesus' paper, especially for the simulation-based methods. And if you want to get your feet wet, I recommend that you take a look at the mini course that I've made available on my GitHub page. OK. So that's all I have for today. If there are questions, I'm happy to take now. Yeah.
So since these are relatively new to the field, if you use this method to solve your PE, what do you expect to report in the paper and in the appendix?
Oh, that's an important question. Okay. The first thing you need to report is numerical accuracy, because a lot of papers don't report it, and it's not clear if the model has actually converged, and the authors are just presenting what they found midway. So please report numerical accuracy, and also a bit on the details on architecture. And thirdly, and most importantly, I think Sebastian would agree, if you found some tips and tricks on learning, please put a note so that it will be helpful to the other researchers. Yeah. Yeah.
Just a high-level question. Sorry. Yeah. So the primary advantage of this method is that you can deal with very large state space efficiently. Can I understand that this?
That's right. That's right. Any more questions?